Start recording. So this is the first session. So we're gonna go over session 6.2, 6.3, and 6.4. So basically, this one is just talking a lot about logarithmic function and its derivative, and also the same thing for exponential function. So logarithmic function, we have the derivative of ln of absolute value of x is 1 over x. And so from that, we have the integral of 1 over x dx is ln of absolute value of x plus c. Doing the same thing that we have with the chain rule, then we're gonna have the derivative with respect to x of ln of u, with u is a function of x. Then you have, it's gonna equal 1 over u times du dx. And the same thing that we have the integral. Oh yeah, this one is not the same. So this one is when you have a more general case where you have log of base a. So then you're gonna have derivative of log base a of x is going to be 1 over x times ln of a. To be honest, I don't think you're gonna see this form regularly, but just in case that you're given one in the problem statement, then I would just put it there for you for like reference purpose. And then we have a very important technique called logarithmic differentiation. Now this one is a technique that allows us to take derivative of very complex functions. Say you have y is equal f of x. Usually is in this form of g of x, and then the entire thing in to the power of h of x. And so this one is usually a hard one to find. So say if you were given the function x to the x to the x, then you should know how to find the derivative by first using this technique. You take ln of both sides. So if you take ln of both of these sides, you're gonna have ln of y is equal to x ln of x to the x. And so by keep doing the same thing, then you can eventually simplify it to the case that you can take derivative of both sides, and then you have something with this term. Then you can find what is y prime. So the second step, differentiate with respect to x. So that's when you take derivative of both sides. And so derivative of ln of y is y prime over y. So you're gonna take derivative until you get whatever y prime is. Then you can do some algebra and solve for y prime. I'll talk a little bit clearer about this in the example, but that's generally it's the idea. Then we have exponential function. So exponential function, we have derivative is of e to the x with respect to x is e to the x. And then the same thing when we use chain rule. Then we have this additional term of du over dx. It gives us the integral of e to the x dx is itself plus c. This is one of the simplest form of integral, so it's really easy to remember. So I would highly recommend remember this additional form. So instead of base e, we have base a, which h is any number that's not 1. So the integral of ax dx is going to be a to the x over ln of a plus c. This one is usually not provided, so I would recommend remember, because it's really helpful in case if you're given something like 2 to the x times sine something, where you have to use integration by part, which you're gonna learn in the upcoming lectures. But this is gonna be really helpful. And then finally, we have the corresponding derivative for that. Now, having said that, let's start with the first example so you guys can see what I mean. So I think from Math 140 last semester, you might have learned about the technique of U substitution. And if not, please feel free to refer back to the book. I think it's the chapter 5 or 4 where we learn about antiderivative and what is integral. And so it's just a very basic technique. If you spend some time looking at the example in the book, I think it'll be really easy to understand. If not, please feel free to email me, because it's part of my job that do the review on the materials for you guys. So okay, so the first one, after we've learned about the derivative of, say, d dx of ax, then we can immediately see something that is very easy to put into u substitution is this part. So we have the integral from 0 to 2 3 to the x multiply square root of 3 to the x minus 1 dx. Now if we literally just find this, trying to find something that will give you derivative of this in the expression, then it will be really difficult, because there is no basic integral that will give you that. So what you are gonna have to do is that you have to use technique. And what I'm gonna do is that I'm gonna put u equal 3 to the x minus 1, or you can put it as square root, it doesn't really matter. Then you have du is going to be 1/2, because this is 3 to the x minus 1 to the 1/2. Then you have 3 to the x minus 1 to the negative 1/2 multiply 3 to the x ln of 3 dx. Now this one, if you do a little simplification, then you can put this integral in that form, in some form that is really easy to find. Another way you can put u is 3 to the x minus 1. Then you have du is going to equal to 3 to the x ln of 3 dx. Now you have also need to do the change of variable. You have 0 to 2. So when x equals 0, u is equal to 3 to the 0 minus 1, which is also 0. When x is equal to 2, u is 3 to the 2 minus 1, which is 8. Then so we have I is going to equal from 0 to 8. Now we try to represent 3 to the x dx in the form of u. We're going to have it equal to du over ln of 3 times u to the half. Now it will be easy to find the integral now. 0 to 8 u to the 1/2 du. Because this part is just the integral of a polynomial, which we have the general formula to be x to the n dx, which is going to be x to the n plus 1 over n plus 1 plus c. But now we have a definite integral, so we don't need to care about that c part. We just need to plug in the value. So you have 1 over ln of 3 times u 2/3 u to the 3/2 from 0 to 8. And what you're going to find is going to equal 2/3 ln of 3 multiply a to the 3/2, which is going to be I'm just going to write it a to the 3/2, and then you put 0, and it's just going to be 0. So it's going to give us, I think, is 2 square root of 2 cubic. So it's going to be 8 times 2 square root of 60. 32 square root of 2 over 3 ln of 3. So this is the final answer for this example. So the general idea here is know how to use u substitution and this part. So because always when you take u substitution, next step is that you always have to take du to do the full conversion of the quantity here, because everything here is now in x. You have to change everything into u if you want to do the u substitution. And so just from this step to this step is where we use the exponential derivative. Now let's go to the second example. So most of the example I'm going over today is going to use u substitution with in addition with what we just learned about log function and exponential function derivative. So again, I'm gonna, oh, okay, so let me go back. So when x equals 0, you have 3 to the 0 minus u equal 3 to the 0 minus 1. 3 to the 0 is 0. 3 to the 0 is 1, so 1 minus 1 is just going to be 0. So is that clear to you? For this u, if you put u in this way, then your change of variable in the first way, so you got your change of variable here is going to be still 0 here, but here is going to be 2 square root of 2. That's why I didn't really continue this way. But I mean, this one should give you the same answer. It's just going to be a little bit more lengthy and involved with calculations. So now is going to example 2. So example 2, evaluate the integral of dx over x times ln of x to the 9. So I think there's one additional, some more property of log that's very helpful, and you guys should also remember it. So in this case, I'm trying to introduce to you, when you have ln of x to the a, and you know x is positive, then this ln of x to the a is gonna equal to a times ln of x. So that's one very useful thing to know. When you have ln of x to the a, you can and you know the x, or even in the very general case, if you have ln of u to the a, with u is a function of x bigger than 0 always, then you have this one is also equal to a ln of ux. So in this case, I would still call this integral to be I. But before I start to do any u substitution, the first step, I think, and I would say, try to do this for as many problems as you can, because it's going to help you simplify the problem a lot. However, there are some cases that you need to keep the form to keep like x to the 9 instead of putting it out into 9 ln of x, so that you can solve the problem. But that's going to come, but to know which one to use is going to come a lot from your practice. And I mean, it's still my practice right now when I have to start a problem in a few steps and try to foresee what's going to happen after that before I do it to the end. And I think it's a very good practice to see apply that. I wouldn't really have a general rule of where you're going to use what. So you're going to have, give me a second. I think I have a frozen screen right now. So since this one is not a very good one to actually, so okay, give me a second. Okay, now I'm back to the stage. So it's going to be x times 9 ln of x. So our integral now is going to be just finding dx, 1 over 9 of dx over x ln of x. Now, this one is where we're going to use the derivative of log. So if we put u as ln of x in this case, we're going to have du is dx over x. And so, and we don't need to do the change of the conversion of variable because we don't have the two value of u over here. It's a indefinite integral. So you're going to have I equal 1 9. So dx over x, now we can get rid of this part, which is du over u. And so this one again is going to be 1 over 9 ln of absolute value of u plus c. This is a part where you're going to see how u substitution helps a lot in this case, because the answer now is going to be u times 1 over 9 ln of x plus c. So in this case, you cannot really like delete this absolute value because you don't know if ln of x is going to be positive or not. So in this case, when I run from here to here, I kind of like subtly assume that x is bigger than 0. But I cannot assume that for ln of x because I don't know the boundaries here. So this is example 2. So I'm going to go to example 3 now. Find the integral of from 1 to e square of ln of x square. This is a square over x dx. And so it's going to be very similar to the previous one. In the, just the only difference is that you know how to do the change of variable. So I'm going to go over this one quite quickly. So I'm going to put u equal, again, the very simple thing is that since you know the derivative of ln of x is going to be dx over x. Looking at this one, if you want to immediately get rid of this and try to do some u substitution, the very first thing you're going to do is you're going to put u as ln of x. Du is the dx over x. Now, let's do the change of variable, since this is a new thing. So 1 and e squared. So u is ln of 1, so it's going to be 0. And then ln of e squared, and this is when you're going to use the thing that I said when you have ln of e squared. This one is going to equal 2 ln of e. I put this 2 outside, and ln of e is just going to be 1, so it's going to be 2. So your I now become the integral from 0 to 2, u squared du, which you can easily take integral to be, yeah, this is from 0 to 2. So this is going to be a over 3. So if I'm going too fast or too slow, please let me know so that I can adjust the speed. But I would assume that you guys can follow whatever I'm saying if you didn't really say anything. So it's example 4. Example 4 is evaluate the integral of sine 2x over 1 over cosine square x dx. Now, this one it's just like a quick review of u substitution. It doesn't really have any new material, but this is when you're going to use the double angle formula. So from here, from what I've done so far today, one rule of thumb that you're going to see in my practice is that at first thing I'm going to try to put them in the same variable as much as possible. What do I mean? It means that say, let's see here, you have 1 plus cosine square x in the denominator. However, in the numerator, you have sine of 2x. If you want to actually solve the problem, you have to put this one into some form of maybe like sine x and something of cosine x. So this is what I'm going to do. That's why I'm saying you're going to use the double angle formula. When you have sine 2x is 2 sine x, multiply cosine x. So now, when you do u substitution, so my u, if I put it as 1 plus cosine square x, my du is going to be 2 cosine x times negative sine x. This is the trick of the technique, and this is what I'm gonna show you. Like, there are some ways that you can take u substitution. So in this case, if you take u as cosine square x, your du is going to be the exact same thing, but it's not going to help you to simplify the problem. And so it's sometimes very important in the way that you take u so that you can do the most in simplifying the problem. And so I'm not going to put u equal cosine square, but I'm going to put it as u equal 1 plus cosine square x. So my I now is going to become my sine 2x is equal to this. My du is equal to this, except for the negative. So I'm going to have negative du over u. So my integral right now is going to be negative ln of u plus c, which is going to be negative ln 1 plus cosine square x plus c. So from here to here is where we use the integral of log, but from here to there is the trick of doing U substitution and know this double angle formula. And it is going to be very helpful in this class, at least in midterm 1, because this is when you're going to use a lot of integration and you do a lot of technique. So it's really helpful if you know the double angle formula. I'll give you also the double angle formula for cosine. Cosine 2x is 2 cosine square x minus 1 is also equal 1 minus 2 sine square x, or it also equal to cosine square x minus sine square x. And this slide is going to be posted after this session ends, so don't worry about copying them for now, but just know the fact that you have the double angle formula for sine 2x and cosine 2x as well. So that is example 4. I think, let me see how many examples. Okay, one more and we're gonna be done for today. Yay! So the last example is evaluate the integral from 0 to 1 of x to the e plus e to the x dx. Now, at first, this problem and before this lecture, this problem will look a little bit challenging for you, but I think it's going to be easy now, if you get the idea. So your eye now. First thing I'm going to do, since these two doesn't really have anything to do with one another, x to the e is in the form of x to the n, but n here is equal to e. But e to the x is exponential function. So they might look very similar, but they're not the same. So if you can keep this spirit of distinguish them, then it's going to be really helpful in solving this problem. So I'm going to separate them now. So I is going to be equal the integral of 0 to 1 of x to the e dx plus the integral from 0 to 1 e to the x dx. I apologize for the noise around here, but it's like 6 a.m. in Vietnam right now, and everyone's rushing to school, so I apologize for the noise. So for this one, again, we're gonna use the general formula of x to the n dx. To find the integral of this is going to be x to the e plus 1 over e plus 1 from 0 to 1 plus this one is just going to be e to the x. Integral of e to the x is just going to be e to the x from 0 to 1. So this is going to equal to 1 to the e plus 1 over e plus 1 minus 0 plus e to the y minus e to the 0. Now be careful here. Don't just think that, okay, when you plug in 0, it's going to be 0. You're going to lose some part of your final answer if you do that. And it happens a lot in this class, at least in midterm 1, because a lot of time people think that they're just going to plug in 0 and it's going to give them 0. And so they miss a lot of part in their answer. But thank God in the exam and quizzes, most of the things are in multiple choice, so you can have a little bit hint on that. But if you see any weird -1 or +1 in the answer, check if you have already plugged in 0 and you thought that's going to be 0 again. And so in this case, it's going to equal e minus 1. And then, so if you want to further simplify this answer, it's going to be e squared over e plus 1 for this entire thing. And so that is the end of our problem. So just a note in here is that after what you learned today, do not confuse x to the e and e to the x. If you can keep them apart and distinguish them by put them into the correct function that they're in, then you wouldn't be confused. One is polynomial and one is exponential. Other than that, that's everything I have for today. I have some practice problems that I'm going to post it in the end of the slide, so please feel free to try them out. And also, I would highly recommend do all problems in the book. And if you can get access to the website of the math department, I think they have on the website of the math department, I think it's like math math141.psu.edu. And if you open the course of Math 141, they have a lot of practice set that is all, like most of them are more challenging than what we're than all the thing that we're gonna touch in this class, but it's all relevant topic. So if you're comfortable solving these and trying to look for some more challenging problems, or you want some extra practice that can like really push yourself through this class, is so you should try both the problem in the book, my practice problem, and also the problems on this website. It's usually more challenging, but if you're good with them, I think you're in very good shape for every single midterm because their problems are quite challenging. Now, that's all I have today, and I'm gonna end the sessions now. I'll see you guys next week. Have a good weekend, guys.